Okay, so we've also brought up the definition of a complete graph and so on, but let's bring up the definition of a connected graph. So if you're connected to somebody, you know them in some way, and it can either be through a friend of a friend or so on. So a connected graph just basically means that it's a graph where every single vertex is connected to every other vertex in some way, in some walk. So, it can be through other different vertices that you get there, but you are connected in some way. There's a path or a walk between you guys. Whereas a complete one, you are adjacent to every person. So you know every person personally, kind of a situation. So a connected graph, there exists a walk, UV, between every vertex or vertice in the graph. Now, given what we know about those adjacency matrices to the powers, there is actually a way where you don't actually have to go look and see, like draw your graph to see if it's connected or not. And that's utilizing the idea that if you sum all your different adjacency matrices, so you say you take your adjacency matrice plus your adjacency matrice to the power 2, plus your adjacency matrice to the power 3, and so on, if you end up with a non-empty, like all the elements of your matrix are non-zero, then it's going to be connected. So what exactly is that saying? So it's an idea or an approach that if there exists a k element in, so that when you sum your adjacency matrix plus your adjacent matrix to the power of 2 plus your adjacency matrix to the power of 3 plus all the way to your adjacency matrix to the power of k, and there exists a situation where all your elements in the summation of your different, all your matrices is not equal to 0, so all your elements are not equal to 0, then G is connected. So this is the way to go about it. It's not always the easiest way because you have to keep on taking your powers of your matrices to actually look at this and go through it. But it kind of does make sense when you think about it, because what is this first matrix telling you? It's given you all the walks of length 1 from Vi to Vj. Then you have the next one, and it's given you all the walks of length 2 from Vi to Vj. So the idea is that at some point, if you keep on finding the walks of different lengths, at some point, if you have it so that all your elements are non-zero, that means that there exists some walk, either of length 1, length 2, length 3, length 4, whatever, from that vertice to the other vertice. And the moment that that happens, it means that it is connected. So just to elaborate on that, because it can be a confusing idea or concept, let's go back to that V1, V2, V3, V4, and let's just draw that in. Okay, if you had to look at that graph, can you find a walk from V1 to V2? Yes, you can say V1, V3, V2. Can you find a walk from V1 to V3? Yes, V1 to V3. Can you find a walk from V1 to V4? Yes, you can say V1, V3, V2, and V4. And if you look at that, this one is of length 2, that's of length 1, this is of length 3. So we already have A, the adjacent matrix, we have A2, and we have A3. So let's just write those down. So we have AG, plus a 2g plus a 3g. So we can actually, well, we should hopefully see if we sum the elements of the different matrices from the raised powers, it should give us a matrix with no zero elements. So we can actually go through there. We can get from V1 to V3, we can get from V1 to V2, we can get from V1 to V4, we can get from V3 to V4, etc. So this graph is connected. And we can show it's connected by just summing A, G, the adjacency matrix of G, the adjacency matrix raised to the power 2 of G, the adjacency matrix of G raised to the power 3. Okay, so I just filled in all the matrices. So this one basically is telling you all the ones of walk 1, a walk of length 1, all the ones of walks of length 2, and walks of length 3. So when you're looking at the adjacency matrices, obviously if they're not all ones there, except for the V1, V1 or V2, V2, then it is not going to be a complete graph because every vertice is not directly adjacent to every other vertice. But that doesn't mean it's not connected, because then you can be like, okay, can I take a detour along my friend's house and then reach, like cut across their house and reach someone else's place? Yes. So you move on to walks of length 2. And then you look at the walks of length 2. And again, there are still some zeros there, but it's not like a massively huge deal. But at the moment, say you just had to add these two together, you would have 1, 1, 1, 0, 1, 2, 1, 1, 1, 1, 2, 1, 0, 1, 1, 1. So at the moment, there's still elements of this. In the words, V1 is not connected to V4 yet. So you can't connect V1 to V4 via a walk of length 1 or walk of length 2. So then you move on to walks of length 3 and you check. And now if you go ahead and add, your walks of length 3 to this situation, you're going to get 1, 1, you have your 2 plus your 1, your 3, you don't really care about that. The fact that that 1's coming in is useful. And again, at the bottom, that 1's coming in, which is useful. So you're going to get all the rest to have values given to you already. I'm going to do this very lazily. But the whole idea is you could stop at this point because every element of this matrix C is non-zero. So there is a walk of length 3 from V1 to V4. And that's what this was basically saying. It was saying there was no walks of length 1 from V1 to V4, no walks of length 2 from V1 to V4. But now we looked and we can find a walk of length 3 from V1 to V4. If, for example, that was still 0, we would continue. We would look for walks of length 4 between V1 and V4 to see if it's connected. And you would pretty much just keep on going to see if you can get like a finite stopping point. And if you can get a finite stopping point, that means your graph is connected, which means there is a walk from every vertice to every other vertice.